So good afternoon, everyone. Thank you for joining our today's presentation. So today we are having one presentation from our series C2M2 CPS Frontier series, and I will like to invite Dr. Mhafuzul Islam, our Center Director, to introduce our today's guest speaker. And after today's talk, we will have a question and answer session where you will be able to unmute yourself to ask your questions, or you can type your question in the chat box at any time, and we can read it to the speaker at the end of this session. So with that, I would like to welcome Dr. Choudhury to introduce our speaker.
Welcome everyone. This is our C2M2 CPS Frontier series. Today, Dr. Mhafuzul Islam will give a presentation on a hybrid quantum classical machine learning for cloud-supported in-vehicle cyber detection. So this project was funded by C2M2. I'm very proud to say that he was my PhD student. Here is a short bio for Dr. Islam. Dr. Mhafuzul Islam is currently working as a senior researcher in General Motors R&D in the US. He received his PhD and MSc in civil engineering from Clemson University and BSc degree in computer science and engineering from the Bangladesh University of Engineering and Technology. His research area includes transportation cyber-physical systems with an emphasis on data-driven connected autonomous vehicles. During his PhD and MS, Dr. Mhafuzul Islam worked under the supervision of Dr. Mashroor Choudhury and worked on multiple C2M2 funded research projects. He previously worked as a senior software engineer at Infineon Technologies in Germany. It's my pleasure to welcome Dr. Islam. Actually, he is fondly known here as Dr. Quantum because he has done some pioneering work on quantum computing, especially quantum AI. So, Dr. Islam.
Thank you. Good afternoon, everyone. And thank you for inviting me for this talk. Actually, previously I was one of the audience and now I'm the speaker here. So it's really an honor and a dream come true to be part of this lecture series. So thank you, Dr. Choudhury, and thank you, C2M2, for inviting me. So let me share my screen. Okay, do you see my screen?
Yes, yes, we can see.
Yes. So as Dr. Choudhury mentioned, I got my PhD in Clemson University and worked on C2M2 funded projects. Currently, I am working as a senior researcher in General Motors R&D in the Vehicle Systems Research Laboratory. And today I'm going to talk about one of the projects that I worked during my PhD that was funded through C2M2. The project that we did was using the quantum computers to solve a classical problem, especially more focused on using the quantum classical machine learning and how we can use that quantum classical machine learning to detect an in-vehicle cyber attack. So please feel free to interrupt me if you have any questions. This will be more like a discussion rather than a talk. So that's why I will feel more comfortable. So before going in details, let's talk about what is this quantum computing actually. So currently the quantum computers that we are using is called classical computers, and it is built on like silicon semiconductors. So this power of this classical computer is increasing, but at some point of time in near future, we'll be limited by this computational power. This is happening because of the data being produced currently. For example, autonomous vehicle produces like gigabytes of data in a second or in a day, in a second, because it has like LiDAR sensor, camera sensors. Those are very high definition data source. And due to this data sourcing, the current computers will be limited to process that data. So that day is coming, and we are facing this issue actually nowadays as well. To solve this problem, quantum computers can play a major role. Why? Because the quantum computer works differently than the classical computers. So quantum computers uses the properties of light or a photon to carry out the computation. In some of the later parts of my slides, I'm going to explain how that works. And in quantum computers, the computational unit is called qubits, the quantum bits or qubits. In classical, that is like we call it bit, 0 and 1. And that qubit can be an infinite, we can have infinite possible linear superposition. In the later of slides, I'm going to describe some parts of it. And using this possibility, we can carry out a larger computation and gain quantum advantage over the classical computers. So in terms of quantum computers, and in terms of machine learning, the data is one of the major source of machine learning. So we can now we can take 4 approaches for this machine learning and quantum computers. So one is the data generating device, and one is like data processing device. So for example, approach number 1 is the classical way that we are doing now. Data is being generated from classical computers, and the data is being processed in a classical computer as well. So in this 4 combination, currently the work that we are trying to focus on is data generating device will be classical computers, and data processing device will be the quantum computers. So let's dig deep into how really a quantum computer works with the properties of light. So we know this double slit experiment. That is the basis of this quantum machine learning. Let me annotate here. Okay, yeah. So for example, we have a particle source that is the photon particles or light source. And we have 2 slits that has a particular distance. When the light goes fallen into the detector here, it can create constructive interference and destructive interference. So intensity of light will be higher in middle of this slit or the detector. And though this is a constructive interference, and where it will be like dark, or this is called destructive interference. So basically what's happening here, that you will have some patterns of constructive interference and destructive interference. And if we consider this probability of or intensity of light source, in the middle, you will have a higher probability of getting the photons. So this is the basic of the double slit experiment. To take it into the next step, we can think of quantum computers having multiple slits. Like here, for example, there are 4 slits or multiple slits, and each of multiple like layers, or each of them has 2 slits. And we can position these slits in different positions. For example, this slits is here, but in the second layer, the slits are in different position. And this way, we can generate a distribution like this and that distribution can represent a classification, or in terms of like machine learning, it can produce a distribution which can represent the classical data. So, and this process, we can think of this process like these layers is different layers of neural networks, and these slits are the passes or the weights of these layers. So by iteratively experimenting these positions, we can get different kind of distributions on the right side. And this setup is called parameterized quantum machine learning, parameterized quantum computers, or we can say it in terms of data, parameterized quantum machine learning. So here we are. I'm just going to show you how it is similar and different than classical computers versus the quantum neural network. So in classical neural network, we have inputs and we have outputs, and the input goes through some hidden layers. It carry out some of the computation, like linear algebra types of computation, and we get a output in the last layer. In the quantum neural network, we can have a similar kind of setup where we'll have the input layer and the output layer and hidden layer. But in the hidden layer, we'll have some kinds of computation that we call it unitary operation. In the later slide, I'm going to present you some of the examples of unitary operation. As this is quantum layers, so quantum computers, in the layer output layer, we measure the output. We iteratively go through go through this. The input comes in the quantum computer, goes through the hidden layers, and then we measure a output in the output layer. So let's dig inside the what's inside this particular quantum neural network. Let me explain you one by one. So as I mentioned previously, a qubit can be in several combinations of zeros and one. So, and that is called a superposition. Mathematically, we can represent a superposition state like this. So qubit can be in 0 state and 1 state, and alpha and beta can be like probability of alpha is probability of having a qubit in 0 state, and beta is the probability of having the qubit in 1 state. And that is, so depending on alpha and beta, please note that alpha and beta is not like binary number. So these are like probability. So that's why then 0 and 1 can be in infinite, we can have infinite combinations or infinite possibilities of a superposition state here. So this input layer, the qubit takes an data as input layer in this form and then performs an unitary operation. So what is an unitary operation? Typically, an unitary operation is performing some rotation, like identity operation, like bit flipping, rotation, and phase shift. So, and mathematically, this can be represented here. So for example, if I take a qubit and multiply with the identity operation, you will have the same output. If I take a qubit and multiply with this bit flip operation, the state of the qubit will be reversed. So this is equivalent to the NOT gate of a classical computer. So in summary, like what happens is that we have some input and we perform the unitary operation, and then at the output layer, we read out that output from this quantum neural network. So, and this quantum neural network has been tested on several studies recently. For example, in the study, like in a study by Fari et al., they have developed this parameterized quantum neural network, and they try to solve a handwritten dataset, MNIST, and they were able to formulate the theoretical foundation of these quantum computers to solve this handwritten dataset classification. And also, like there are some recent development in terms of developing the tools. For example, TensorFlow provided by Google have developed a TensorFlow quantum library that can, using that, we can develop this quantum machine learning models. So the domain that we are trying to focus on, classical problems. But can we use any classical problems, or can we use can we take a classical problem and solve it using the quantum computers? So our goal is to select a real world problem and solve it through the quantum computers. So in terms of let's think of a classical problem that happens in real world. Typically inside a vehicle, we have different ECU, that is electronic control unit, and they communicate with each other using a bus system that is called control area network bus, or CAN bus. So what happens is that if some of the ECUs or one of the ECUs get compromised by an attacker, then the in-vehicle system will malfunction. So in terms of severity, it can create an accident or some kind of malfunction of the system. This domain is being explored, and we see that in the studies like Tesla or some other vehicles can be compromised. Even the GM vehicle was compromised remotely by an attacker. So the attacker can reside locally or remotely as well. And one of the studies that we did previous to these quantum studies, that how we can solve or detect this in-vehicle cyber attack. So we call this cyber attack, we call this in-vehicle cyber attack. And in one of our previous studies funded by C2M2, we explored how we can solve this, detect a cyber attack using classical neural network. So this is the problem domain that we are trying to focus. And the cyber attack that we considered is an amplitude shift attack. So different ECUs communicate with each other, and one ECUs, the ECUs creates the data. And what happens that in the amplitude shift attack, the value of that particular ECU generated by the ECU get compromised, and it can be shifted up and down. The problem here is that this kind of attack is very difficult to detect, because the value is being shifted, but the pattern over the time remains the same. For example, here in the red one here is an attack data. It is just shifted from the original value by 2, but you see the pattern here, like there is a 2 peaks here. These are the same. So as the pattern is same, it's very hard or difficult for a classical computer to detect. And our studies have found that using a LSTM neural network, long short-term memory neural network, we are able to detect this kind of cyber attack with an accuracy of 87.9%. Still 87.9, that means there is a possibility that it will not be detected. So what's the solution of it? So due to the limitation of the quantum, there are some few limitations to the quantum computers before I proceed, because we cannot run the quantum computers inside a vehicle. That's why we rely on a cloud supported or a cloud infrastructure to run the quantum computers and solve the classical problem. So for example, when the attacker is attacking the data or the CAN bus that is connected to the cloud, and when the CAN data goes into the cloud, it can run the quantum neural network here, and say and analyze the data and return that if there is an attack or no attack on the data. So it's the quantum neural network is running inside the cloud, and the vehicle is running in real time on the field. So how do we proceed with the quantum neural network? So we have the CAN data set that will be used. That is the classical data source, and that will be used to train our quantum neural networks. First, what we do is that we use a classical neural network to for extracting some of the features from that data. Then the classical neural network gives the data to a quantum neural network, and we train the hybrid quantum classical neural network. Then we perform the analysis and results from it. So I'm going to unfold each of the items here. So one of the challenges that is using the quantum computers is quantum computers can only execute quantum data. What it means is that if we have a classical data, we cannot directly use it in quantum computers. So to do this, we need to convert the classical data into quantum data. And then after the conversion is done, we can feed that quantum data into a quantum computer, and quantum computer will generate a quantum results. But how do we interpret that results? Again, we need to convert these quantum results into a classical results. So that is that pipeline using a classical pipeline for solving a classical problem using quantum computers. Also, one of the limitations of quantum computers is that the quantum computer has limited number of qubits. For example, I think we have now 8-bit real quantum computers, as IBM and others are also working in this area to extend the capability of quantum computers. But in terms of like solving the real world problems, number of qubits are limited. So that is another challenge here. So that's why like we need to convert the classical data into a quantum data so that the data can be executed by the quantum computers properly. To do so, in terms of okay, so we collect the data from the CAN data. So this is just the overview of a hybrid classical neural network, hybrid quantum classical neural network, where we produce a CAN image, and that is a classical input, 13 by 13 data, and we use this feature extractor from that image to downsample it by 4 by 4. Why we are downsampling it? Because of the limitation of qubit. Because 13 by 13 is 169 data points, and quantum computers cannot support that number of qubits yet. That's why we need to downsample the data to 4 by 4. So that means the quantum data, quantum computers will have 16 qubits to process the data. So 4 by 4 classical data needs to convert it into a quantum encoding, goes to a quantum encoding to convert it into a quantum data. So classical 4x4 data goes in, we perform quantum encoding to convert the classical data into quantum qubits data. And then 4x4 quantum data goes through quantum neural network, and then it gives an output like one by one output, where we say if there is an cyber attack or not, 0 and 1. So this kind of setup, like some part in a neural network, some part are in classical domain and some computation are in the quantum domain. And we call it hybrid, and that's why we call it hybrid quantum classical neural network. So I'm going to like more in details how we do it. So in the first step, we prepare the CAN image data set. So that is a classical data, and inside the classical data, CAN data, we have different features. So CAN image, for example, if this is a raw image, we have in the CAN image, we have an ID, and this is the payload of the data, and we have a timestamp. And after we analyze the data, we see that there are 13 features, prominent features, that is safety critical, and they are interrelated. So that's why we take these 13 features of the data. For example, like one of the feature is like brake ACT, that is brake actuation, and it has a value between 0.0 to 3. So we take these 3 and we convert this we put these 3 features from feature 1 to feature 13 in one row for a single timestamp. And we take continuous 13 messages and we stack them horizontally to get a 13 by 13 image. So why we do this actually? Because CAN data is coming in real time. It's a time series data. And that's why we take a particular time. Now we collect the data of 13 messages, that is the time series data, and perform this vertical stacking and horizontal stacking to get a 13 by 13 image. So moving on, we perform the feature extraction. That is the first part of the hybrid classical quantum computer. We take 13 by 13 CAN image. We take a neural network, that is convolutional neural network, and create a 4 by 4 feature image. Again, why we are downsampling it? Because 4 by 4 quantum computers cannot take 169 input, 169 data points as an input. So that's why we're downsampling it to 16 points of data points. This neural network is in performing in the classical computers, and we have used the pre-trained CNN to extract the features from this input 13 by 13 CAN image. Then we perform this quantum encoding, and this is one of the representation of this quantum encoding. Quantum encoding is like we use the basis quantum encoding that I'm not going to details in it. So for example, if we see in the attack data, so this is a normal data and this is an attack data. In a normal data, we have less number of variations, but in attack data, we have higher numbers of variations that we observe. So this is a classical representation of this quantum data. This quantum data is going to be used as an input to the quantum neural network. let's see how really quantum neural network works in terms of like training. As I mentioned before, uh, we quantum encoded data goes into a quantum neural network, and inside quantum neural network we can perform unitary operations, and this can be considered as different layers and parameters of this quantum neural network. So the process of training a quantum neural network is conceptually same as a classical neural network, where we have the data level, uh, we have the input data, we have the ground truth like the data level, and after going through this one pass, feed forward pass, we perform a back propagation to fine tune the parameters of quantum gates. So in terms of the first, it performs a computer. So after it goes first pass, we calculate the gradient and the loss, and based on how it performed, we update the parameters of the quantum neural network, like each of the gates here. So it's more like we are going through first pass and coming back again is a few like back propagation. We are in the back propagation cycle, we are updating the parameters of quantum neural network. So after we perform the training, we do the testing on the test data set, and for the testing we have performed the comparison between three candidates, that is like our developed hybrid quantum classical neural network, and then only quantum neural network, and then the LSTM neural network from the existing literature. So as you see that in the hybrid quantum neural network, we have a feature extractor, that is a convolutional neural network to perform a feature extraction. But in the quantum only neural network, we just do a resizing of the data, but do not perform any neural network, but rather than we just resize the original data from 13 by 13 to 4 by 4. And number 3 is the LSTM neural network. That LSTM neural network is a classical neural network which has different layers. And this LSTM neural network can do the analysis, is developed especially for the time series data, as the CAN data set is a time series data, that's why. So on that, when we do this comparison, we optimized each of the neural network so that all of the candidates that we are comparing here performs at their best level. For the hybrid quantum neural network and quantum only neural network, we have the number of qubits 17. The 17 is because we have 16 qubits and 1 qubit for the measurement, for control measurement. So that's why we are using 17 qubits quantum computers, and we vary the number of epochs, number of layers, and batch size, so that each of the neural network performs at their best. Please note here that one of the things that we have come up with is that number of trainable parameters. So for the LSTM, the number of trainable parameters is almost like 1 million. where quantum neural network, where quantum only neural network has number of parameters 128, and using a hybrid classical neural network, the number of parameters is 96. So the meaning is that we need, we require a less number of hyperparameters so that each of them is performs as that best. And reducing that means is that reducing the computation actually also. So when number of parameters is equivalent to number of computation, so we are reducing the computation of each of the networks as well. And on the testing data side, testing data, ultimately what we want to detect is that how accurately we can perform this cyberattack detection. So previously I mentioned that LSTM neural network has accuracy. That we use that LSTM neural network and perform this on our testing data set, and it was 87.8% accurate in detecting this cyber attack, where hybrid classical neural network was accurate almost like 94%. If we take only quantum neural network, that is in the middle, it was very less accurate. It was only 62% accurate. So here, there are two reasons that is happening here. One is like we are using this hybrid setup. The classical neural network is extracting the features, and quantum neural network is also performing the feature extraction and prediction, the detection, cyber detection. So that is more robust in detecting a cyber attack. So two advantages here actually. So we are using less number of parameters, and with a less number of parameters, we can achieve a better cyber attack detection accuracy on this data set compared to classical LSTM network and quantum only neural network. So, but the reason that we concluded that why this is happening, the reason is that the extracted features from the classical neural network allows the quantum neural network to explore the more features or neighboring features in a large space. Because of the nature of the qubit, we can have a infinite possible combination, infinite number of possibility to explore the features. And we concluded that this neural network with an hybrid setup has a potential of replacing the classical machine learning models in future. And and at the end, like I would like to thank C2M2 for funding this research. It was really a nice time that we explored this, and we are able to achieve some good results. So with that, I like to thank everyone for their attention. And if you have any questions or if you want to discuss, please shoot me an email. With that, I'm going to hand over to question answer. I'm going to the question answer session.
All right. Yeah. Thank you, Mahfuz, for the informative presentation. So at this point, we are open for the question and answer session, and you can always type your question or unmute yourself and ask the question. So I will start just to give some time to the audience so that they can prepare some or think of some questions. So one question that I had, Mahfuz, is that like in the quantum only model, so the feature extraction that mapped the 13 by 13 to 4 by 4. So was it done by that 13 by 13 qubits?
Um, so here, quantum only neural network, we take an image like 13 by 13,
Yes.
and we resize it to 4 by 4.
Yes.
So we don't extract any feature using classical, like using any CNN or something. So
Okay.
we just resize the data.
Oh,
And in the process, actually, we lost some um, like prominent features from it, actually.
okay. And
So yes, please.
sorry to interrupt. Just is any specific process that you did to do this resizing, or it was just syncing the data?
It was like a standard resizing from the library functions, like from
Yes.
Python.
Okay.
So like I used OpenCV for doing the resizing of that image.
All right. So, Dr. Dixit, do you have any question?
Yes. So as you are saying, so earlier image was 13 by 13, and then you resized it, and after that you got 4 by 4 image, right? Okay. And then you use some autoencoder to reduce its dimension after resizing it. Did you use that?
So that encoding, actually, like quantum encoding, so that takes like a classical bits and converts it to a quantum data. So
So what do you mean by classical bit? So is it like in decimal number? So here your data is like between 0 and 1, right?
yes,
And then you convert it into binary, right? 0 or 1.
right, exactly.
Okay.
So here is one of the binary representation of the data.
Yeah. Okay. So like black part is something 0
Zero.
or 1, and white is okay. So it is either 0 or 1, right?
0 or 1, right?
Yeah. So can you go to previous slide one more time?
Sure. Here,
Yeah,
right?
yes. So, so your can image size of your can image was 13 by 13, right?
Right.
So can you again tell something more about can images? How you got these can image?
Yeah. So actually, like in every CAN image is a time series data, so it's coming continuously, right? Um, and as we are dealing with the time series data, that's why we cannot just feed one data. So we take a chunk of data, create an image, and then it goes through the neural network. So, and we continuously collect 13 images, and we have the features, the prominent features, 13 features, and we stack them up horizontally, like the time series data is stacked up horizontally, and the vertically we take the features of each of the data.
Okay, so you converted this data into image, you can say, right? Okay.
Right.
So you converted time series data into image data, and then you performed analysis. Okay.
Right, exactly.
Okay. Okay, yeah. Thank you. Yeah.
No problem. Thank you, Dr. Vivek.
Thank you.
So we have an independent course that we are offering this semester, and students from that course, everyone is attending this seminar.
Nice.
Yeah. So the students, do you have any specific question? Now it's a very good time to ask and to Dr. Islam about the applications, right, of quantum AI. So do you have any question that about a project or any confusion, or do you want to discuss an idea that you want to pursue?
Hi, Dr. Islam. So I have a quick question. So recently, as we were doing a demonstration for the adversarial attack detection on the AI model. So yes, and also we did a virtual traffic light demonstration. So while we were using quantum models, so the issue that we have been facing is that the quantum models sometimes they're computationally not very fast because the competition is very complex and they take a lot of time. So I wanted to ask you, so because you have extensively worked on the hybrid classical quantum model, so what do you think about the real-time implementation of these models, and how we can if there are any shortcomings of these based on the current technology, how in future we can improve them so that we can efficiently implement them for real-time cases in the real world scenario?
Actually, that's a very good question and very valid question. And that is also one of the concern in the current research community, to use this can we use this quantum computer in real-time application? The answer is not yet. The answer is no, or not yet, because how it works is that due to the hardware limitation, we cannot do it we cannot do the quantum computation locally, like inside a vehicle or inside like we use as a computer. Currently how we do it two ways. One is like using a simulated quantum computers and using a real hardware. And using the real hardware, access to real hardware is very limited, because like IBM or some other suppliers only has the access to these real quantum computers. The issue with that is that we need to get access to it, we need to go through a process like submitting the job through cloud or their online platform, wait to run it in the quantum computers and get the results back. Definitely this is not real time. The second approach is like simulated quantum computers. On that simulated quantum computers, runs on the classical quantum computers. So we can run them locally, or we can run them like the IBM quantum computers or something like this. But still that is not real time. So this is one of the challenge actually that researchers is working on, to get the quantum computers into a shape that we can run it locally. So apart from this, there's another challenge is that the real quantum computers needs to be in a controlled environment, and even if we have the real quantum computer, then the noise or like decoherence or like stability of these computers make it stable is a very challenging task actually. So it requires a controlled environment currently. So, and due to this, not all of the application will produce a desired outcome, like the one that we call is quantum advantage. So the domain is very specific actually, like the problem domain that we want to solve in quantum computers is very specific. For example, like very specific domains like chemical compound production or decomposition that we do in chemistry field, or like optimization, which is hard to do in classical computer. That can have a advantage using quantum computers. We can achieve quantum advantage using in this particular area. So how to overcome this is like, I would say that's the task of our researcher to tackle these challenges and come up with the solution. So this is a open field, or more of the research is ongoing. So I see that it will come ultimately. and that's my vision as well. And I envision that it will come eventually, but it will take some time. Hope that answers your question.
Yes, thank you, Dr. Islam. Thank you very much.
Thank you, Sabir.
Hello, Dr. Islam. I have one question.
Yeah, sure.
For the training quantum network, you have showed that we have 16 data, but we have taken 17 qubits. And one of the final qubits was doing something. So I want to inquire what it was doing. And for the post layer, when you're saying that we are measuring in the classical part, are we measuring all the 16 qubits or just the last extra qubit which you have introduced during the training of quantum neural network?
Okay. Nice. Good question, Rick. So let me just here. Maybe I'll try to answer this from this slide, and I'll try to explain what's going on. So we have 4x4 data, that is 16 data points, 16, and we can say that is 16 inputs to quantum computers. And there is one extra qubit that is used for the control of the measurement. So for example, if this is 1, then we perform the measurement. If it is 0, then we don't perform the measurement. So that's how it in total is 17 qubits. Sorry, what is your next question? Sorry, I forgot.
Yeah, so I suppose you are telling that the 17 qubit controls the measurement, right? So my question, are we doing 16 qubit measurement or 17 qubit measurement?
Oh, okay.
In
Yeah,
the post measurement layer kind of thing.
Right. So here you see that in this image actually, so it's like 16 input, 16 output. But the one that we implemented had one output only. So that has one, so because the neural network is like convoluting to one output, and we are measuring only one qubit at the end. And so the answer is that the input is 16 qubit, but the output we get from the quantum neural network is one output. Yeah. Does that answer your question?
Yes, sir.
Thank you, Rick.
Yes, so any other question? We still have some more time. So the students, if you want to ask some other questions, if you don't have any question, then we can then conclude today's session. So with this, I want to thank Dr. Mhafuzul Islam for this very informative presentation, and also breaking out the different components and of these quantum neural networks. So it's very easy to understand with this nice visualization. So thank you for the effort. With this, I will like to conclude today's session. So this video recording will also be available in YouTube. And if you have any question or if you want to reach out to Dr. Islam, just let us know, and we'll help you guys to reach out to him for any further question related to today's talk. So thank you very much, Mahfuz. Have a great rest of the day, and thank you very much all for attending and to make this event successful event.
Thank you, everyone.